Let's look at a little bit more complicated case. We talked about control hazards due to jumps. Let's put the control hazard one cycle later. And a good example of that is something like a conditional branch. So here we have a piece of code, add branch, and it's branching to 200 bytes into the future. If you take 100, branches on MIPS are relative to the subsequent instruction, so it's PC plus 4 plus the offset, so we're going to end up at 304. And let's walk through this case here. We have I1 is our first add. We have the branch sitting at the decode stage. And we have some decode logic, which is saying, is this a branch? OK. The next question, though, is how do we compute whether this is a branch is being taken or not? Can we do this in the decode stage? Unfortunately, we need to do a comparison here. And this comparison, the hardware we want to use to do the comparison is in the ALU. It's a subtract operation or a comparison operation. So this fits well within our arithmetic logic unit. And we have the 0 wire coming out. So what this is going to do is instead of having one cycle of latency or one cycle of kills being inserted, we might have to insert 2 cycles. Because now we have to wait for the branch to get to here. And if we are predicting PC plus 4, we're speculating PC plus 4, we will actually have fetched more data. So let's walk through this. So the branch moves forward one cycle forward here. And what you'll see here is we're actually fetching 108. So we're fetching the next instruction. But these two are both potentially dead. We want to kill both of these. But we don't know whether to kill them until we get this 0 wire here. OK. So at that point, we can redirect the front of the pipe, and we can insert a no-op. So that's going to change the logic that connects to here. We're also going to have to insert a no-op here because we fetched 104 at that time into this point of the pipe. So if a branch is taken, we need to kill the next 2 instructions. And the instruction at the decode stage is effectively invalid. So we need to swing this mux here. So we're going to have to add an extra control line onto this multiplexer. And now, stalling and killing makes a lot more difference. So the stall signal has to effectively be killed or nullified at this point. And why is this important? Well, let's say we're stalling the front of the pipe and stall were to take priority. That would stop this register from moving and stop this register from moving as this red lines come in. So if the stall were to take priority, you could have an instruction here, which is, let's say, dependent on some stall condition or dependent on some data hazard or dependent on some random hazard. And you have a branch which is branching to someplace else. So let's take this instruction here, 104, which is an add, is dependent on something that's stalling the front of the pipe. But at the same time, you want to kill because you took the branch. You want to kill that instruction. If you were to put the stall at the higher priority, you would actually end up with a deadlock because you'd be stalling, but you would have no way of killing the previous instructions to clear the stall. So this is why it's really important that the instruction at the decode stage is now invalid. So unlike the jump case where, well, you might be able to do either way with the priority of the stall and the kill wires, here the kill has to take precedence, or the redirect has to take precedence. And that's going to redirect the front of the pipe and basically clear out everything here. And if you were to stall it, you would not be clearing it out. So instead, you need to kill, sort of turn these all into no-ops, and redirect the front of the pipe to go fetch the actual target of your branch, of your conditional branch. Yeah, sorry, this is just drawing now that this branch information has to go into this multiplexer and go into this multiplexer. The other thing that's important here for branches is we need to figure out the address that we're actually branching to. And we'll talk about this more when we get to branch prediction later in the course. But what you're going to have to do is you have to take the PC plus 4 and add it to the branch offset. Because on something like MIPS, there's PC relative branching. And the other thing is we can't reuse this ALU necessarily to do that. You could potentially reuse this ALU if you were microcoding your design. But unfortunately, we need this ALU to do the branch comparison. So we need to add another adder here to come up with the target of our branch. Now, some people get smart on the way they build this. And you can actually see some things where people will try to reuse the main processor pipeline ALU to do the branch offset calculation, and maybe try to do this comparison, because if you have simple enough branches, you can do the comparison with less hardware than a full adder. That's another option. Let's hold off talking about that until a little bit later. OK, so now we get to talk about the stall signal in detail. So we start off in blue here at the top, the stall signal we had from before. So you need to check the data dependencies and check for data hazards between the registers of the source operands. These are the R, S, and RT in the decode stage against the other stages in the pipe, the execute stage, the memory stage, and the write back stage, and make sure that you're both reading the registers and you check the write enables to make sure that the respective instructions in the different pipeline stages are actually writing to the different locations. But now we add another term. We add a branch term. So we need to know whether there's a branch going on here, because we need to unstall the processor if the branch is taken. So we're going to add not, and this is effectively, it is a branch 0 and 0. Likewise, it's a branch not 0, and the value is not 0. So these two terms are basically saying a branch is happening, it's in the execute stage, and we'll say that the branch is being taken. So if it's a 0 branch and the result is 0, it's taken, or if it's a not equal 0 branch, it's not taken. And why don't we stall if the branch is taken? So it's the same question we had on the previous slide. You have a branch, it's happening. If we stall the front of the pipe, the instruction of the decode stage has to be unstalled to get that out and to clear it out. So the instruction of the decode stage is now invalid, so we don't want to pay attention to any of the stall information. It's just like a red herring, or it's a piece of information you shouldn't be paying attention to. So you want to have the instruction of the decode stage be turned into an invalid instruction. OK, so now we get to talk about the control equations for the program counter and the instruction register multiplexers. So let's start off by talking about PC source. And so I want to remember what that is. That's way up here. It's the input to this multiplexer. And that's going to select where we're branching to, or excuse me, not necessarily where we're branching to, but the program counter of the next instruction we're going to fetch on the next cycle. And it's on the next cycle because this is a flip-flop. So a little bit of control equations here. Just I wanted to point sort of two basic things out in this these equations is that the older instruction, or the thing that's farther down the pipe, is going to get precedence over younger instructions, and for the control signals going down the pipe. So if we look at this PC mux select, it actually has things coming out of different stages of the pipe. We have something which is redirecting for a jump out of the decode stage. And then we have these signals here, which are coming out of the execute stage, which is strictly farther down the pipe. And this needs to take precedence over that. So if you have a branch which is directly followed by a jump, the jump's going to be sitting there trying to sort of swing the control on the PC select mux, or the next program counter mux. And you can't let that happen. You have to let the branch that's actually executing take precedence over that. And that's really what we wanted to get across from this. And you'll see that similarly here, the branch takes precedence over the jump and link for the other control signals. Let's look at this from a branch pipelining perspective. So we'll draw the pipeline diagram for a branch executing for our example. And what you're going to notice real fast here is if you take a branch and you actually execute the branch and take the branch, you're going to be adding 2 extra instructions here, in this case 104 and 108, and they get killed as they go down the pipe. And this is going to impact our CPI in a negative way. And what's happening is this execute, the branch which is in the execute stage, is going to reach back and kill these instructions inserting the no-ops. And we can plot this in the other dimension also, but you'll see. So now we need to think hard. Is this a good thing? Well, we speculated that the instruction was, or the next instruction was going to be PC plus 4, or the address of the next instruction was going to be PC plus 4. So we took something where the CPI was, let's say, 2, machine with CPI is 2, and we cut it down a little bit in the common case. But jumps, the CPI still goes back up to 2. And here, the CPI is 3. Now, in our speculation case, or our no speculation case, if we had a branch, we would probably have to stall for 3 cycles anyway to know the destination of that branch. So this didn't really hurt us in that case. The CPI in that case was also 3 for a branch instruction. OK, well, but this still isn't good. I don't want every single branch I take to have a CPI of 3. So let's talk about some ways to mitigate this cost. Or how do we reduce the branch penalty? Well, one way to do it is we can actually add a comparator one stage earlier and have it resolve in the same timeline as something like the jump. So how do we do that? Well, here we have our register file. This is in the decode stage of the pipe. This is the fetch stage. What do we really need to do for a branch? Well, we need to know that it's a branch. So we do some decode. And we need to know whether it's a branch 0 or a branch not 0, for instance, if those are the only 2 branches in our architecture. And we need to know that, let's say, register 1 is 0 or not 0. So some people came up with this smart idea that we can add a 0 detector onto the register file output. And by adding the 0 detector into the register file output, we'll know which way the branch goes. So the 0 detector, one of the interesting things is this is actually a little bit easier than doing a full comparison with 0. Because to do a 0 detect, you can basically build a optimized OR tree and then either take the negation of it. And sometimes people even do this with sort of wire doors or more analog-y circuits. But this is effectively a big OR gate where you OR in all 32 bits if you have a 32-bit processor, and then take the NOT or take the bit itself. And this is easy for zero detect. This can get harder for different types of branches. If you have something like a branch equals or BEQ instruction, you can't use zero detector. What you have to do instead is somehow actually do a full comparison between two of the source operands. And that usually takes more time. So the nice thing about this is that it'll take all your branches and take them from a CPI of 3 when they mispredict or when you misspeculate to 2 cycles with the same timeline that you had with a jump. So you end up with the exact same pipeline that we had for jumps now. The downside is that this is going to elongate your cycle time, because you have this wire coming out, and the wire needs to go into the logic which computes PC source, and this can become a critical path. And it's a critical path because you have to go through the decode. That's usually done in parallel, but you have to access the register file, then go through a zero detect, and then go into the control logic which computes this, and then come around and latch the information or flip-flop the information. So you can really negatively impact your clock period. And as we talked about the iron law of processor performance, you can either get performance by lowering your clocks per instruction, or you can get it by lowering your clock frequency. Or excuse me, increasing your clock frequency or lowering your clock period. So these two things trade off. So you can elongate your cycle time, which will negatively impact your performance or time per program in our iron law of processor performance. But on the flip side, you will have branches resolve faster. So your clocks per instruction or your aggregate clocks per instruction, especially for branches, will go down. So this is only one approach. Another approach is you can expose it to software. So we can change the instruction set architecture. And what's really cool here is the instruction set architect can actually have an impact on what's going on here. This is not all microarchitecture issues. It's not all fancy branch predictors, as we'll be talking about later in this course. But instead, you can expose this problem or this challenge of the time it takes to resolve a branch to the software. So what we're going to do, I'll define a branch delay slot. And a branch delay slot is a architectural, when I say architectural, I mean big A architectural or instruction set architectural change, which allows or forces some number of instructions after a branch to always execute. So it could be, let's say, 1, 2, 3, or 4, some number architecturally defined. And in this delay slot, that instruction is executed irregardless of the direction of the branch. And what people try to do with this is they'll try to take work that was above the branch and move it below the branch. Because if you know the work's going to be done anyway, you can just put it below the branch and everything's OK. But the problem with that is the branch has to not be dependent on that work that you're moving below the branch. So typically, for very short loops, where there's not much work inside the loop, this becomes very problematic, because there's not enough work that the branch is not dependent on to move below the branch to have the loop run effectively. And what we're trying to do here is the compiler has a hand in what's going on, or the program writer really has a hand in what's going on, because that's what's doing the reordering of the information from above here to below here. So let's take a look at an example here where we have a branch and we have one delay slot. Some architectures have 2 or more, but right now we'll assume one delay slot. And let's also assume that we have this reduction of branch penalty optimization. So now branches only have one dead cycle when we're going to execute them. So what we can do is we can say, OK, the branch is at address 100. And this add here at address 104 in the delay slot executes irregardless of whether the branch gets taken or falls through. So then we don't actually have to kill the next instruction after the branch. We don't have to have all this fancy extra hardware there. We just have this always execute. The tricky thing is many times, as I said, it's hard to fill this branch delay slot. It'd be great if you could have many, many branch delay slots. So if you go look at something like a Pentium 4, I think they have a 20-odd cycle mispredict penalty. They could have added 20 delay slots to their architecture. That would have been really, really cool, but at the same time, the compiler would have to go find 20 instructions for every branch to stick after the branch. And there's usually just not that much work to be put after the branch, which the branch is not dependent on. So we have a really hard time filling these branch delay slots. And roughly, if you go look on something like MIPS across sort of old spec ints, to give you some example here of how often the compiler can actually fill branch delay slots, I think the rough rule of thumb is if you have one branch delay slot, you can usually fill it maybe about 70% of the time on something like spec int. Spec int is a common benchmark suite that's used throughout the computer architecture industry or the computing industry to measure performance. And if you have two branch delay slots, that second branch delay slot only gets filled less than like half the time. So if you're only filling these slots relatively infrequently, you might be better served by coming up with other prediction mechanisms. And we're going to talk later in class about, not this class, but in a different lecture, branch prediction, which is a technique to cover branch latency and to make a branch decision early, where we can predict whether the branch is being taken or not taken. And this can be used to dramatically reduce the branch penalty. So let's draw the pipeline diagram here of a branch delay slot. Or architecture has one branch delay slot. So we have the add flowing down the pipe, we have a branch flowing down the pipe, and now we're going to have this next add, and architecturally we've defined that always executes whether the branch is being taken or not taken. So this code sequence, or excuse me, this pipeline diagram sequence here is the same for whether the branch is taken or whether the branch is not taken. In this case, we're going to say that the branch is taken, and we go to execute this next add here. But you'll see that there's no bubbles. There's no no-ops being inserted. So we've actually improved the performance here. This is assuming, though, that this add is doing useful work. Now, this is really important to say because the compiler or the program writer has to put something here. And if they can't put anything useful, they're going to have to put no-op. And that's not useful work. Doing a no operation, you might as well just have had the hardware insert the no-ops for you and save some instruction coding space. So there's tough trade-offs here between how often you fill the branch delay slot versus having a branch delay slot. But for right now, we'll say branch delay slots are one good technique to put useful instructions after a branch and not have branches stall a lot.